In our next section, we're going to start to combine what we previously saw in our MPLS example with BGP routing and also with the virtual routing and forwarding instances, the VRFs, put these together to form our final solution, which is the layer 3 MPLS VPNs that are BGP based. Now in this section specifically, we're going to talk about what are the different components in L3 VPN, where does VPN v4 fit in, where do the route distinguishers and route targets fit in, and then what is the difference between the transport labels and the VPN labels. We'll take a look at some basic configuration examples, and then in later sections we'll start to get into the details of what are the different L3 VPN designs in terms of what are the PE to CE routing variations, what are the intra-AS versus inter-AS options, and then for inter-AS, what are the different ways we can do exchange in terms of options A, B, and C, both for L3 VPN as well as for L2 VPN. Now, ultimately, layer 3 VPNs for MPLS have two basic components. We have the separation of the customer routing information, which is going to be based on the virtual routing and forwarding instances. And then we have the exchange of this information within inside of the service provider that is going to be based on BGP. Now, we talked about specifically what the VRFs do in terms of separating both the control plane and the data plane on a per interface basis. We're then going to combine this with the BGP routing over the MPLS core in order to exchange the customer routes for beyond multiple hops. Because with our previous example in VRF Lite, when we want to exchange the information in the routing table, we have to do this on a hop-by-hop basis. So what I mean by this is if we go back to our previous design in the topology, we had a case where we were running a VRF Lite config that went between router 4 and XR1. We had this in VRF A. And let's assume that we want to exchange this information down to router 7, that it's going to be in the same virtual routing and forwarding instance. So this means that we would have to run an instance of VRF A between router 7 and XR3, an instance of VRF A between XR1 and XR3, another instance of VRF A between XR1 and XR2, basically on a hop-by-hop basis to get all the way to whatever the final destination is that we're trying to reach. So the problem then becomes within the service provider core, we don't want to have every single hop along the way know about the final customer routes and have to define this VRF on a hop-by-hop basis. So the solution for this then is to combine these two features together, where we're going to be running BGP between the service provider edge routers, the provider edge routers, and we're going to exchange the customer information encoded into a new BGP update. And this is going to be accomplished through two things in the BGP update: the route distinguisher plus the prefix, which makes up the VPN v4 routing information, and then the MPLS VPN label, which is going to be an extended community attribute of the actual BGP update. Now, from a high-level overview, when we look at the total steps in order to form the MPLS L3 VPN, the first thing we need to do is to make sure that we establish a label switch path between the provider edge routers. So in our particular case, if we're going to say that our PEs are XR1 and XR3, this means that we already have to be running IGP routing between them, which is typically either going to be either OSPF or IS to IS. And then we have to run some sort of labeling, which is typically going to be the label distribution protocol. And again, as we previously saw with LDP, the main advantage of this is that it's very plug and play. That under the OSPF process or under the ISIS process, you simply say MPLS LDP autoconfig, and it's going to run the protocol everywhere. The end result is that whatever IGP routes we're advertising, we also have an MPLS label bound, so we have an any-to-any full mesh of label switch packets or label switch tunnels. Okay, next step would be that we have to exchange the routes with the customer. So in our particular case, this is going to be from XR1 to router 4, from router 3 to router 7, from router 2 down to router 10. We need to be running some type of control plane routing exchange between them. This could be IGP, this could be BGP, this could be as simple as static routing, could be policy routing. Doesn't really matter, but we have to run some sort of VRF-aware protocol in order to get the routes in from the customer to the service provider edge. Now, once we've accomplished that, we then need to take these routes and exchange them between the PE routers within the MPLS network. So this means that we're going to be running iBGP, and we're also going to be advertising an MPLS VPN label for these routes or more specifically, we're going to be running the VPN version 4 address family between the PEs. Now, in our previous examples of internal BGP routing, the same logic is going to carry over for VPN v4 BGP, where we could either do a full mesh of iBGP, we could do route reflection, we could do confederation, just as long as somehow we advertise the routes between the PE routers and we use the next hop of the BGP update to send our traffic towards the MPLS tunnel. That is ultimately how we're going to be separating the traffic in the data plane when the customer traffic transits over the service provider core. So the very last step is going to be this actual label switch path, the LSP. So the LSP is going to be following the IGP plus LDP tunnel, or what we refer to as the transport label, between the loopbacks of the provider edge routers. Now, we'll see in later examples, once we start to get into details of troubleshooting L3 VPN, this is one of the simple ways that you could cause problems, that if for some reason you're advertising the route with a next hop value that is not reachable via a label switch path, it means that ultimately the customer's traffic over the MPLS core is going to get dropped. But again, the simple way to prevent against this is that if we're running IGP plus LDP everywhere and we're advertising our loopbacks into IGP, it should mean that we have a full mesh of connectivity everywhere in terms of our label switch paths. Now, specifically, the way that we're going to be exchanging the updates between the provider edge routers is an extension to BGP that's defined in RFC 4364, which is BGP for MPLS virtual private networks, where specifically this is going to be a new address family identifier and sub-address family identifier, which is 1/128, which we commonly refer to as simply VPN v4. Now, VPN v4 routes are going to be adding a key attribute to the update, which is what we call the route distinguisher, or the RD. Now, the RD, we'll see that we can have this as a unique value per provider edge router, but at a minimum, we have to have this as a unique value per customer. So typically, one customer, VRF-A, is going to get route distinguisher 1:1. A different customer, VRF-B, is going to get distinguisher 2:2. And then from a BGP path selection point of view, this is the way that we're going to keep the traffic separate in the control plane. Now, in addition to the actual routing update, the VPN v4 route is also going to include the MPLS label. This is the way that we're going to keep the traffic separate in the data plane. So when we specifically look at the VPN v4 network layer reachability information, or the NLRI format, we're including the route distinguisher, the IP prefix and the length, the next hop in the MPLS label. Beyond this, the rest of the BGP attributes are going to stay the same as if it was a regular IPv4 unicast route. So this means things like the weight, local preference, AS path, origin code, MED, the communities, the processing of those in the BGP policy application would remain the same from IPv4 unicast to VPN v4 unicast. The main thing that we really care about that has been changing is the route distinguisher, which makes the route unique, and then the VPN label, which is ultimately going to control how we forward the traffic in the data plane. Now, as I mentioned previously, the reason that we use the route distinguisher is that multiple customers might be advertising the same addressing information into the BGP network. So let's say, for example, that the customer attached on router 6, let's say that router 4 is customer edge, router 5 is customer edge, and router 7 is customer edge. It's 10 as well. So we have between router 4 and XR1, XR1 is the provider edge router. Let's assume that we're receiving the network from router 6 that is 10.0.0/24. And we'll say that this is going to be in VRF-A. Okay, we also have customer router 7 who is in VRF-A. We're advertising this 10 network from XR1 over to router 3. We're advertising this in a BGP VPN v4 update. And then we have another customer that's router 10 that is advertising in VRF-B the same prefix, 10.0.0/24. So if router 2 advertises this update over to XR1, again through VPN v4 BGP, from a BGP path selection point of view, XR1 would get confused to say, well, which customer really owns this route? If both of the routes are equally 10.0.0/24, I'm not going to be able to tell the difference between them. And how do I know that I'm not advertising to router 3 that the destination we're going to is really this customer B. This is what the job of the route distinguisher is. So the only thing the route distinguisher is doing is making the route unique. It's additional padding that we're inserting into the front of the BGP prefix to say that when you do your path selection decision, you're no longer doing it against 10.0.0/24, you're doing it against 1:1:10.0.0/24, or 2:2:10.0.0/24. So this means that customer A and B's prefixes, even if the routes overlap, or I should say even if the IP prefixes overlap, the route does not overlap because the route distinguisher is giving it global significance. Now the route distinguisher, however, doesn't control which particular VPNs the route is actually going to belong to. This is what we use the route target for. So the route target is an extended community of the VPN v4 route, and the key is that we can have multiple targets on a per route basis. Whereas the distinguisher, there will be only one per prefix, but the route targets we can have multiples of. What this is going to allow us to do is have granular control over what particular sites will have reachability to each other by using import and export policies that specify who is able to receive, who is able to advertise the routes based on the specific route targets. So this commonly gets confusing though because the route distinguisher and the route target have the same format from a bitwise basis and from a visual formatting. But the main difference between them is that the distinguisher is used to make the route unique. There's only one per prefix. The route target is what defines the VPN membership. There has to be at least one for the route, but there can be multiples. Now, likewise, the route target, like I mentioned, the reason that it's confusing is that it's the same type of field. So it's an 8-byte field defined as a BGP extended community. Format is similar to the route distinguisher, where we have typically the BGP AS number, colon, a locally significant number, or the IP address format of the provider edge router, colon, a locally significant number. Now we'll see that in terms of receiving VPN v4 routes, there is an exception to route filtering, where when you receive an update in, you're only going to accept routes that match a target that is matching your local VRFs. Now we'll talk about this in more detail later. What are the other implications of this in terms of inter-AS routing, whether we're doing inter-AS option B, option C? We'll see that we need to change this filtering behavior around, but you can think of this as an automatic optimization. That if we were to have, let's say, a route reflector design, and let's say that router 1 is going to be our route reflector for the VPN v4 address family. And we have, again, VRFs A on the left, A on the right, A on the right. We have B on the bottom, and we have B on the top. So router 2 is receiving this route in, advertising it to 1. 1 is advertising it over to XR3. XR1 receives this route in from 4. It advertises it to router 1. Router 1 reflects it to XR3. XR3 says, I have routes that are coming from VRF A and VRF B, but I only have VRF B configured locally, so ideally I want to discard those other prefixes. And that's the default behavior of the route target filter. That when you receive an update inbound, you look at the extended communities, and if the route target value does not match a local VRF's route target import policy, you delete the update. Now we'll see later there are cases where you would not want to do this. One of the main ones is when you are running as a route reflector, but the route reflector ignores this filter and it reflects all of the VPN updates to all of the remote peers. But just keep this in mind that this is the default behavior, that you only accept the routes that match against one of your local route target import policies. Now, as I mentioned, additionally, we can have multiple route targets per prefix. This is going to allow us to establish complex topologies, where we can do not only a full mesh of connectivity, where every site has reachability to every other site, but also we could do hub and spoke, we could do central services, where the service provider is hosting a service on behalf of the customer, like they're doing shared mail hosting or shared VoIP, like voicemail hosting. But in the vast majority of cases, we're typically going to have a full mesh of connectivity between the layer 3 VPN sites. But the idea is that we define this by configuring what is the route target import and the route target export policy. Now the VPN update, though, as I mentioned, is used to separate the control plane of the customer, not of the data plane. Because we receive the route in from the customer through OSPF, through BGP, through whatever protocol, we advertise it to a VPN v4 route, and it goes to the other customer sites. Now, once the advertisements are done, then we start to receive the traffic in the data plane, and we need to figure out that if we have multiple customers that are located on the same PE router. So let's say from XR1's point of view, that it has a case where we are attached to customer A on router 4 and customer B on router 8. And let's assume again that they're advertising the same prefix. We have 10.0.0/24 and we have 10.0.0/24. Now we said from a BGP updating point of view, the way that we can keep these separate is by adding the different route distinguisher. We could say 1:1:10.0.0 and 2:2:10.0.0. So now whatever other devices are in the middle, they can say that there's a difference between path A and path B because the route distinguisher is making them unique. However, when the traffic comes in the data plane, the IP packet doesn't know about the route distinguisher. The IP packet is simply going to say the destination that I'm trying to ping is 10.0.0.1. We might have 10.0.0.1 on router 8, we might have 10.0.0.1 on router 4, so somehow this provider edge router needs to be able to tell the difference between the two of them. This is where we see the difference between the MPLS transport label versus the VPN label. So in L2 VPN, in L3 VPN implementations, we need at least 2 MPLS labels in order to keep track of what provider edge router is the traffic going to egress out of to leave the service provider network, and once it gets to that PE router, which customer is it going to go to? Now the first of these, the topmost label or the transport label, is telling the service provider core which provider edge router are we going to use to egress the traffic, or what is the exit point. Now this label is the one that is typically derived from IGP because we're running LDP plus IGP in the core of the network. And this is the one that's saying, well, how do you get between XR1 and router 3? The way we do that is label switch packets to 3333. We label switch packets to 11, 11, 11, 11. And since these routes were already advertised into ISIS or already advertised into OSPF, any of the devices in the core of the network, they should already have reachability to those. Now, once the traffic gets to the PE, though, XR1 needs to say, well, I have packets that are going to 10.0.0.1, 10.0.0.1, but they're 2 different customers. How do I know that? The way is by encoding a second label in the stack. So the VPN label, this is the one that is derived by the BGP VPN v4 advertisement. Once the traffic actually arrives at the PE router, this is the one that tells it what customer is it destined to. So we'll do a secondary lookup once we remove the transport label, do a secondary lookup on the VPN label, and then say, hey, this VPN label really relates to VRF-A on interface gig 00001111, and I now know to forward the packets out there. So we'll see that the key with VPN v4 is that it's separating the control plane information, but then also using this label to encode in the data plane, how are we actually going to forward the traffic when it gets to the egress PE. Okay, so there's a couple questions here. So the control plane is defined by the route distinguisher and the data plane is defined by the route target. The route target and the route distinguisher, they both define the control plane only. What defines the data plane is the VPN v4 label that's advertised in the VPN v4 update, which we'll see in a couple minutes here when we actually do the implementation. How do you tell what number that specifically is? And then where is that going to be used for label switching in the core of the network? But the BGP update in terms of the route distinguisher, that's what's keeping the path unique in terms of path selection. The route target is defining the VPN membership, and then the VPN label is what's keeping it separate in the data plane. There's another question. So the VPN label is created when you start receiving VPN v4 routes for a particular VRF located on the PE via a route reflector. It doesn't necessarily have to be via a route reflector, but it's when you redistribute from the VRF into BGP, or more specifically, when you do a VPN v4 export from the VRF into BGP, that's when the VPN v4 update is created, and that's when the MPLS label is created. So what we'll see specifically in this case is that if router 6 is the final destination and router 6 is advertising updates out to router 4, okay, let's say that we're going to run IGP here. Let's say we're running EHRP that goes between router 6 and router 4 and 5, and then between router 4 and 5 we're running BGP with the provider. So router 4 and router 5, these are going to be the customer edge devices. Router 1 and XR1, these are going to be the provider edge. These updates are going to come in as regular IPv4 unicast BGP, and we are converting them by exporting them to VPN v4 unicast. When we do this export, it's basically like a redistribution from one table to another. When we do the redistribution, that's where we create the VPN label. Then when we do the advertisement, router 1 is going to advertise over to router 3, hey, I want you to use label 1234 in order to get to the destination. And the next hop of the update is pointing towards my loopback. So router 3 is going to say, well, I need to get to 1111 first. I already know this via IGP, and I already know this via LDP. So I'm going to take whatever the IP packet is that came in, and I'm going to put on the top of it my transport label. So the transport label, this is the one that is defined by IGP and LDP. Then after the transport label, I'm going to put in the VPN label. So the VPN label is going to be whatever this 1234 is that was received from the VPN v4 update. Then inside of that, we're going to have the original IP packet, whatever router 7 is sending. The packet is going to be switched through the core based on the transport label. It's eventually going to arrive at the final destination, router 1. Router 1 is going to see the VPN label. It's going to do a lookup and say, hey, this relates to customer router 5, and then I'm going to forward the traffic out to them. So the core of the network is going to be forwarding based on the outer label. The edge of the network is going to be forwarding based on the inner label, the VPN label. There's another question here. Is there a correlation between the VPN label and the route target? No, there's not. So the VPN update will only have one label, but it can have multiple route targets. So whoever is learning the label number, that is locally significant between those two VPN v4 BGP peers. So you may see the number 1234 used again in transport somewhere else, but since it's locally significant between you and your directly connected peer, you will see that it's normal that the label numbers overlap, but they have different significance depending on where they are in the specific label stack. If they're on the top of the label stack, that's the transport label talking about the provider edge exit. If it's at the bottom of the stack, that is the VPN label that's talking about the final customer destination. Now we'll see the logic is going to be similar in terms of layer 2 VPN, where the top label is typically the LDP bound label going to the transport, the exit PE, and the bottom label is going to be the pseudo wire label that is either generated from a targeted LDP session or from a BGP VPLS session, which is going to be a new address family. It's basically address family VPLS or address family L2 VPN. But we'll see once we understand the L3 VPN logic, it's going to be a little bit easier to understand how the L2 VPN logic works. And we'll see the L2 VPN configuration is actually a lot simpler than the L3 VPN is. There's another question here. The VPN label is advertised via multi-protocol BGP, correct?